All right, up to this point, we've only dealt with energy changes within a particular phase. So we've started with liquid water, we've finished with liquid water. We haven't looked at what happens with energy when you start changing phases. And that's something you need to know for honors chemistry. So we've looked at these phase diagrams before, and we can tell that something different is happening with energy whenever we go through a phase change, because we go through these regions where we're adding heat, but the temperature doesn't actually increase. We know that energy cannot be created or destroyed. That energy must be going somewhere, and we need to capture that in our calculations. So that's what today's lesson is about. When a substance is changing state, it does not experience a change in temperature. What is the heat doing if it isn't increasing the temperature? It is going to disrupting or breaking the intermolecular forces that are holding the particles together, either as a solid or as a liquid. Okay, so here we are disrupting intermolecular forces that hold particles together either as a solid or as a liquid. We're going to learn more about intermolecular forces when we learn more about bonding in Module 3, I believe. But for now, just know that this energy is not disappearing. It's going to disrupt these forces that are holding particles together. So in order to do these problems, there are a few numbers we need to know. We need to know that the specific heat capacity for water, which is something we've used over and over again this module, is different to the specific heat capacity for solid water. So liquid water has a different specific heat capacity to solid water. If you've got an ice cube and you apply energy to it, it heats up more quickly than the liquid water does. If you have gaseous water, that heats up even more quickly than an ice cube. So if you apply energy to it, the gas changes temperature even more quickly than a solid or a liquid. So we have different specific heat capacities depending on whether we're talking about a solid or a liquid or a gas. In addition to that, we have to worry about what's happening during the melting phase or the fusion phase, and what's happening to energy during the vaporization phase. And we have different energies to help us look at that. So the heat of fusion, that just means melting. Okay, how much energy does it take to melt water? How much energy does it take to disrupt the intermolecular forces holding a solid together to make it a liquid? It takes 6.01 kilojoules, not joules, kilojoules per mole. A mole is a measure of the amount of a substance. It kind of tells you how many particles, how many atoms you have. It's not in atoms, it's in moles, because atoms are so small, you end up having more than trillions, quadrillions, quintillions. You actually kind of measure them in sextillions. So we've got a lot of zeros in this number. We're going to learn more about the mole later this year. For right now, all you need to know about a mole in terms of water is that when you have 1 mole of water, that's the same as 18.02 grams of water. We'll learn why that is later. So for now, I'm going to give you this constant in a problem. You don't need to be able to derive it yourself. Later on this year, you will learn how to derive that. So our units here are all messed up. When we looked at specific heat, we had joules and grams, and now we've got kilojoules and moles. So we're going to have to use some dimensional analysis when we're looking at these questions to convert from joules to kilojoules or back, and from moles to grams or back. Heat of vaporization, this is going from a liquid to a gas. We'll use this value as well. Notice it takes a lot more energy per mole to get from a liquid to a gas than it does to get from a solid to a liquid. And again, we'll learn more about that when we learn about intermolecular forces. So let's look at an example problem of this kind of problem. So, how much heat is required to take a 25-gram sample of water from negative 10 degrees Celsius to 135 degrees Celsius? Okay, so if we're at negative 10 degrees Celsius, we're starting as a solid, then we'll be a liquid. And if we go all the way up to 135 degrees Celsius, we'll get up to a gas. And we'll go through that melting phase, and we'll also go through the vaporization phase. So there are 5 different stages here for us to account for when we're determining the energy associated, the heat energy associated with this problem, the heat energy required to heat up the water this much. So let's look at each section of the equation. We're going to do solid, liquid, and gas together because those all use the energy equation that we learned before, Q equals C times M times delta T. And then we'll do melting and vaporizing separately. So the Q value for solid water is going to be Cm delta T. So we're going to use the 2.09 for the specific heat capacity because that is the correct specific heat capacity for solid water, times my mass, which is 25.0 grams, and my delta T, which is, let's see, I'm starting at negative 10 and I'm going up to 0. So my final, because that's the freezing point of water, going up to 0 minus the negative 10 degrees Celsius. So my temperature change here is 10 degrees Celsius. We always do final minus initial, remember. I should actually write 10.0 to keep my sig figs correct. All right, so we do the math and we get 522.5 joules as our energy, but that's only accurate to 3 significant figures. Rather than rounding off at this point, just so that I don't carry any rounding errors forward, I'm going to leave this number as it is and just underline the significant figures in each number. Let's look at our liquid next. For our liquid, we're still doing Cm delta T. This time our C value is 4.184 joules per gram per degree Celsius, times my 25.0 grams again. And this time my temperature change goes from, let's see, I end at 100 degrees, but I started at 0 degrees. So that's a temperature change of 100 degrees Celsius. And if I do the math, I get the answer 10,460 joules. Again, the limiting sig fig value here is the mass, so only the first 3 digits here are significant. Lastly, the Q value for the gas portion of the problem. I have a specific heat capacity of 1.84 joules per gram per degree Celsius. I still have 25.0 grams. This time my temperature change goes from 100, ends at 135 degrees, but starts at the 100 degrees. And so that's a temperature change of 35.0 degrees Celsius. When I do the math, I get 1,610 joules. Again, 3 sig figs here. 3 energy values so far. I just have 2 portions remaining, and these ones are perhaps a little less familiar to you. So let's look at how we do those. For melting, we're going to use the heat of fusion here. But before I use the heat of fusion, remember the units that we're going to use involve kilojoules and moles. So I need to know how many moles of water I have if I have 25 grams. So I need to convert 25 grams into moles before I can do my fusion and vaporization calculations. And to do that, I just use dimensional analysis. I start with 25.0 grams. And because of the conversion factors I gave you on the previous slide, you know that 1 mole is the same as 18.02 grams of water. And we get a value of 1.387347, goes on for a little while, moles. And this answer is accurate to 3 significant figures. Although this figure is accurate to 3 significant figures, again, you want to avoid rounding off too soon. If you can't hold in your mind, if you can't kind of do this strategy where you just underline the ones that are significant and deal with them later, another strategy is, well, it's a similar strategy, but you can just go 1 decimal place further, just so that you're less likely to have an impactful rounding error. So, the heat associated with the fusion process of this reaction is going to involve that constant that we saw on the previous slide, this 6.01 kilojoules per mole, 6.01 kilojoules per mole, and we're going to multiply by the number of moles we have, and we have 1.387 moles. That's not the correct sig figs. I'm going 1 further on purpose just to make sure I don't have rounding errors. And doing the multiplication gives you 8.3539. But again, this is only accurate to 3 sig figs. But notice that my units here, the moles cancel out, and I'm left with kilojoules. So right now, as things stand, I cannot add this kilojoules value directly to my joules values. I'm going to need to change one or the other in order to have them all be the same units. But I'm going to have the same problem with my Q of vaporization. So I'm going to hold off on doing any unit conversions yet. My Q of vaporization, this time, the heat of vaporization is 40.67 kilojoules per mole. So 40.67 kilojoules per mole. Again, I'm multiplying by the 1.387 moles. Those moles cancel out. I'm going to have kilojoules as my answer. So if you do the math here, you should get 56.53 kilojoules, and that is only accurate to 3 significant figures. So let's look at how we're going to put these 5 values together. If I add up my 2 kilojoule values, although this has 3 sig figs and this has 3 sig figs, when I add them together, because of lining up decimal places, I can only go to 1 decimal point. So my answer from adding those 2 together gives me 64 point, well, according to the calculator, I have 64.8839, but I have to round that off to the 10ths place. So I get 64.9 kilojoules for this portion of the reaction. And then for these 3 values, if I add up those 3 values, again, when I add those together, I can't go further than the hundreds place because this value is only accurate to the hundreds place. So when I add those values together, the calculator tells me that the sum is 12,592.5 joules, but I have to round off at the hundredths place, so I'm going to have 12,600 joules. I'm going to convert this to kilojoules so that I can add it together with my other value that I have here. I'm going to convert this to 12.6 kilojoules. So now my total Q for the entire change, the entire process, is the 12.6 kilojoules plus the 64.9 kilojoules, and that gives me a total of 77.5 kilojoules is my final answer for this problem. It's a lot to take in. There are 5 different parts to this particular problem because we have 3 different phases and 2 different phase changes. But basically, the Q value for the entire process is the sum of the heat for the solid, the heat required for the liquid, the heat required for the gas, the heat required for the fusion process, the melting, and the heat value for the vaporization. So there are a lot of parts to it, but the process isn't as bad as it may look at first. I hope this helped.